Welcome to the Deep Dive, the show where we take a stack of sources, articles, and research and basically distill them into the essential insights you need to be well-informed, fast.
That's the goal.
Today, we're plunging headfirst into the fascinating and honestly really rapidly evolving world of autonomous mobile robots, or AMRs.
Yeah, it's moving incredibly quickly.
We've pulled together a pretty comprehensive collection of materials here covering, well, everything from their intricate engineering to their truly transformative impact on modern industry.
It's a lot to unpack.
Our mission for you today is to really unpack this technology, give you a holistic understanding of how these incredible machines are revolutionizing manufacturing and warehousing, and fundamentally how they're shaping the future of work itself.
It really is an essential topic right now. We'll be breaking down what AMRs actually are, how they fundamentally differ from, older automation tech, like automated guided vehicles, AGVs.
Right, that distinction is key.
Definitely. And then we'll sort of peel back the layers to reveal the complex technological symphony, that's a good way to put it, that allows them to perceive, move, and communicate with such precision.
And what's really fascinating, I think, is how these robots aren't just about streamlining existing logistics, which they do,
Oh, for sure.
but they're also venturing into entirely new applications, things like proactive industrial surveillance and maintenance, stuff you might not immediately think of.
Exactly. Moving beyond just moving boxes from A to B.
That's where the real excitement starts to build, I feel. And crucially, we're going to examine the human element. How are AMRs creating what people are calling a blended workforce?
Mm-hmm.
What does that actually mean for redefining job roles? And how is this whole thing setting the stage for, well, what they're calling Industry 5.0?
It's a big shift in thinking.
Yeah. So it's a journey from understanding the urgent, really pressing need for automation right now, all the way down to the cutting-edge trends shaping where these robots are headed next.
So let's start right there. The why now moment for autonomous mobile robots. What forces are converging, right now to create this urgent demand for such advanced automation in our factories, our warehouses, our distribution centers?
Well, it really feels like a perfect storm, doesn't it? A convergence of several interconnected factors that have been building for some time.
Yeah, it didn't happen overnight.
No. First, and probably the most visible one for most people, is the just relentless explosion of e-commerce.
Oh, yeah. Unstoppable.
As consumers, we've become incredibly accustomed to lightning-fast deliveries, sometimes same day, next day, and often really low cost, right to our doorsteps.
It's the expectation now, isn't it?
Totally. It's not just a convenience anymore. It's like a deeply ingrained expectation that has completely reshaped the entire supply chain.
Honestly, yeah.
And fulfilling that insatiable, always growing demand requires logistics operations to hit levels of efficiency that were, almost unimaginable just a decade ago.
Yeah, the scale is immense.
And frankly, human labor alone just can't keep pace. Not with the sheer volume and the speed required.
That's precisely right. The sheer volume of goods moving through the supply chain is, well, escalating exponentially. Relying only on manual processes has become a massive bottleneck.
A huge bottleneck.
But beyond just the volume, there's another critical factor, maybe even more impactful in some ways, and that's the shrinking labor supply. It's a global challenge.
Yeah, we hear about this constantly, and it isn't just about finding enough people, right? It's profoundly about finding people willing to consistently do jobs, often described as, well, dull, dirty, and dangerous.
Oh, the triple D threat, as some sources call it.
The triple D threat, exactly. Think about a traditional warehouse job. It can involve long hours, repetitive movements, heavy lifting, maybe exposure to heat or cold, and always that constant risk of injury.
It's tough work.
It really is. And the numbers are pretty stark. Reports are projecting, a staggering 85 million unfilled jobs globally by 2030.
85 million, that's huge.
And that gap could translate into something like an $8.5 trillion loss in unfulfilled annual revenue. Just massive economic impact.
And warehouses are hit particularly hard, as you said.
Disproportionately hard. Workers in today's economy, well, they have more choices. And the physically demanding, often monotonous nature of traditional warehouse work makes it really difficult to attract enough people and then keep them.
High turnover is a chronic issue.
Leads to high turnover, persistent staffing shortages. It's a real struggle for these companies.
Which brings us to a really fundamental question. Are AMRs just, replacing people, filling those empty spots?
That's the fear you sometimes hear, isn't it?
It is.
Yeah.
But what's critical to understand, and what the sources we looked at strongly emphasize, is that they are not just like-for-like replacements. That's not the right frame.
Okay, So how should we think about it?
Think of them as a technological alternative designed to augment and enhance human capabilities. Their core purpose is to take over those really physically demanding, repetitive, and frankly low-value tasks, the stuff that contributes to that triple D nature of the work.
Okay, that's a crucial distinction. So offloading the constant heavy lifting, the miles and miles of walking through a huge warehouse, or the repetitive sorting that frees up the human employees.
Exactly. It frees them up to focus on higher value activities,
Mm.
things that genuinely require critical thinking, creativity, nuanced problem solving,
Things humans are good at.
things humans excel at. Imagine a worker shifting from just moving boxes all day to maybe managing a fleet of intelligent robots or troubleshooting complex system issues that pop up, optimizing workflows in real time, maybe even engaging in strategic planning,
So it's not just about boosting raw efficiency numbers.
although it does that too.
Right. But it's also about fundamentally making the jobs more appealing, maybe increasing job satisfaction.
Definitely. And ultimately, significantly improving employee retention in an industry that's notorious for high turnover. People stay when the work is more engaging and less physically punishing.
And this optimization, this deliberate blending of people and robots, the sources say it demonstrably leads to faster, more efficient, more cost-effective workflows.
Yeah, the results are pretty clear. Companies implementing these solutions are reporting not just those productivity gains, but also increased satisfaction and, interestingly, enthusiasm for work within these new blended teams.
That's fascinating. Enthusiasm.
Yeah, and the adoption numbers really underscore this trend. Over 84% of warehouses and factories globally already use some form of material handling or robotics equipment. That shows a clear, accelerating trend towards automation in general.
84% is huge already.
It is. And looking specifically at AMRs, the newer tech, more than 71% of companies are currently deploying or planning to deploy material transport automation in their facilities.
71% deploying or planning, so this isn't some niche futuristic thing anymore.
No, it's rapidly becoming the standard. It's here now.
Those are incredibly significant numbers, really illustrates a profound shift. The development of modern AMRs has clearly hit a tipping point, hasn't it? Where robots and humans can work together seamlessly, enhancing operations, boosting efficiency.
To unprecedented levels, really.
Yeah.
And as you mentioned earlier, their ability to take on those triple D tasks, the dull, dirty, dangerous ones, that's a major differentiator.
Right.
Think about it. AMRs are designed to perform those really long trips across vast facilities, handle incredibly heavy lifting that would be unsafe or just impractical for humans, and operate consistently in hazardous environments where you really want to minimize human exposure.
Like areas with extreme temperatures or
Yeah.
bad air quality.
Exactly, or places with toxic substances. By taking on these roles, AMRs don't just improve throughput, they also significantly reduce personnel risk and profoundly enhance overall occupational safety.
And that's a key driver for investment in many industries, I bet. Not just efficiency, but safety.
A huge driver, absolutely.
So that really sets the stage for why AMRs aren't just here, but why they're absolutely crucial for the future of industrial operations. But, okay, to truly grasp their impact, we need to dive into what makes an AMR an AMR. How does it fundamentally differ from its predecessor, the automated guided vehicle, the AGV?
Yes, let's clarify that, because this distinction, which often gets confused, is incredibly important for anyone considering automation.
People use the terms interchangeably sometimes.
All the time.
Yeah.
But there's a fundamental difference in their operational capabilities, their intelligence, their flexibility. So let's define them clearly first.
Okay.
An automated guided vehicle, AGV, is, well, essentially a robot that follows a fixed, predetermined path or track for moving materials. Think of it like a train on tracks, or maybe a tram.
Right. Fixed route.
Exactly. It requires significant, often costly infrastructure changes to operate. Things like magnetic tape stuck to or embedded in the floor, wires under the surface, painted lines, or maybe strategically placed visual markers and reflectors that it follows.
So an AGV is rigidly constrained. It can only go exactly where that tracker tape is laid. Like you said, a commuter bus that always follows the same route, no deviations.
Perfect analogy. Now, an autonomous mobile robot, AMR, that's where the autonomous part really signals the leap in capability.
Yeah, the key word.
An AMR operates independently. It intelligently navigates an uncontrolled environment that's key without needing any fixed paths or guiding infrastructure. It's all about inherent flexibility and adaptability.
Okay, no tracks, no tape. So how does that difference play out in practice? Let's get into the key operational differences. Navigation and obstacle avoidance must be huge ones.
They're probably the most significant distinctions. AGVs possess minimal onboard intelligence. Their primary function is basically to detect an obstacle on their fixed route, and if they do, they just stop.
Just stop dead.
Stop dead and wait until that obstacle is manually removed by a person. This can, as you can imagine, grind an entire operation to a halt if a pass gets blocked.
Right, a pallet falls over, a forklift parks in the wrong spot. The AGV just sits there.
Exactly. And furthermore, modifying an AGV's route is a costly, disruptive, and time-consuming process because you have to physically alter that infrastructure, rip up tape, reprogram markers, etc.
Okay, so very inflexible. But AMRs, this is where it gets really interesting. They're loaded with tech, right? Cameras, sensors.
Absolutely. They're equipped with advanced intelligent navigation capabilities. They leverage an array of cameras, sophisticated sensors like LiDAR, which uses lasers to map, and 3D depth sensors, laser scanners, all integrated with powerful software.
So what does all that tech let them do when they encounter an obstacle?
This is the magic. It allows them to dynamically adjust their routes in real time. They detect and safely maneuver around obstacles, whether it's a temporarily blocked route, an unexpected delivery pallet, a human worker walking by, or even another robot. They don't stop.
They just go around.
They intelligently reroute. They find an alternative path without stopping the flow. This ensures continuous material movement, maintaining efficiency even in dynamic, unpredictable environments like a busy warehouse floor.
That flexibility sounds like a complete game changer. AGVs, being stuck on their routes, are pretty limited in application then.
Inherently limited, yes.
Yeah.
They're typically programmed for a single repetitive delivery task. And like we said, altering their function or route just isn't cost effective because it demands that significant, often disruptive infrastructure overhaul.
So basically, an AGV is built for one specific, unchanging job for its whole life.
Pretty much. An AMR, on the other hand, offers unparalleled flexibility. It can perform a wide variety of tasks at different locations within a facility, often with just simple software adjustments.
Software changes, not ripping up the floor.
Exactly. Missions are usually controlled via an intuitive interface or, more commonly now, a sophisticated fleet control software system. This system prioritizes orders and assigns tasks dynamically based on the robot's real-time position and availability. It's much smarter.
And what if the facility layout changes, like they move production lines around?
That's where AMRs really shine. They can quickly remap a site or just upload an entirely new building map, often in a matter of hours or maybe a day, not weeks or months like with AGVs. This adaptability makes them absolutely ideal for agile businesses that constantly need to optimize and evolve their operations.
Okay, flexibility is huge.
Yeah.
What about safety? How do they compare there, especially with people walking around?
Safety is another critical point of differentiation, and frankly, a major advantage for AMRs in modern mixed-traffic environments where people and robots share space.
Yeah, that seems vital.
AGVs, remember, primarily rely on basic sensors designed only to stop when an obstacle is detected right in front of them. This often requires manual human intervention to clear the path and restart the robot, creating disruptions. Their rigid nature can definitely disrupt workflows and potentially create hazards in busy, human-centric environments.
So they're reactive, not proactive about safety.
That's a good way to put it. AMRs, conversely, are designed from the ground up for safer, more flexible operations. They use advanced sensors, high-resolution 3D cameras, LiDAR, AI-driven obstacle detection algorithms to navigate dynamically and avoid obstacles proactively rather than just stopping reactively.
So they see further ahead, understand the context better.
Yes, they intelligently adjust their speed based on the environment, they reroute smoothly around obstructions, and crucially, they comply with stringent international safety standards like ISO 36914.
ISO 36914, what does that cover?
That standard specifically addresses the safety of industrial trucks, including AMRs, and their interaction with humans. It mandates things like predictive collision avoidance, not just reactive stopping. It's a much higher bar for safety.
Okay, that's a really important difference. And then there's the cost and the return on investment, the ROI. People might assume the fancier AMR tech is way more expensive upfront.
That's a common assumption, but it's often misleading when you look at the total picture. AGVs typically do come with a higher initial investment because of all that extensive guiding infrastructure. You have to install the wires, the tapes, the floor modifications.
And the disruption cost while you install it?
Exactly.
Oh.
That installation process itself often causes significant production disruption, leading to further hidden, indirect costs. Plus, their inherent inflexibility means ongoing expenses down the line if you ever need to adapt or change workflows.
So the upfront cost of the AGV robot might be lower, but the total cost of getting it running and adapting it is higher.
Often, yes. AMRs, despite their more advanced technology, frequently turn out to be more cost-effective overall in the long run. Critically, they don't require those extensive disruptive modifications to your existing building infrastructure.
Ah, so deployment is faster and cheaper.
Significantly faster and more affordable deployment. AMRs can often be operational within days or weeks, not months, so they start improving efficiencies almost immediately.
And that means a faster ROI.
Much faster. Companies frequently report achieving a full return on investment in less than 6 months, sometimes even quicker.
Wow, less than 6 months. That's impressive.
It is. And furthermore, they're inherently scalable. As your business grows or your needs evolve, you can simply add more robots to the fleet or repurpose existing ones for new tasks just through software updates. Minimal additional infrastructure cost, unlike AGVs, where scaling often means more construction.
Okay, that makes a lot of sense. And we've seen some big players really validating this, right? Like the BMW Group example in our sources.
Yes, BMW Group is a fantastic real-world case study. They are truly pioneers in embracing AMRs on a large scale. They specifically chose IdealWorks AMRs over traditional AGVs for their highly complex production environments.
And not just in one factory.
No, across multiple plants, Regensburg, Dingolfing, Munich in Germany, Spartanburg in the US, with plans already rolling out for share in Austria, Hamshall in the UK, and Leipzig in Germany.
So a major strategic decision across their network. Why did they make that choice?
It wasn't a casual decision, as you said. It was based on the clear, demonstrated superiority of AMRs, specifically in mixed traffic and brownfield settings.
Brownfield meaning?
Meaning existing facilities, often older ones, that weren't originally designed for automation. Environments that combine human workers, existing infrastructure, maybe uneven floors, places where that flexibility and adaptability of AMRs are absolutely paramount. AGVs just struggle in those complex, imperfect environments.
And the impact at BMW, the numbers were pretty staggering.
Nothing short of remarkable. They currently have nearly 600 of these IdealWorks AMRs, the RW hubs, operational.
600 robots.
Yep, undertaking an astounding 30,000 missions per day across their network.
30,000 deliveries or tasks every single day.
With an impressive 98% availability rate. That means they're running reliably almost constantly. This has truly revolutionized their internal logistics, leading to significantly enhanced efficiency, flexibility, and safety across their globally distributed production network. It's a powerful testament to the transformative power of AMRs when deployed strategically and at scale.
Okay, so we've firmly established why we need AMRs and what fundamentally makes them different and better in many cases than older automation. Now let's really get into the weeds. How do these incredible machines actually work? What's going on inside an autonomous mobile robot that allows it to navigate, communicate, and operate with such, well, autonomy?
Right. Let's peek under the hood. It really is a technological symphony, a combination of sophisticated systems working together seamlessly.
So where do we start? The brain.
Let's start with the brain, yes. At the heart of an AMR's intelligence is its ability to understand its environment and know where it is within that environment. This relies heavily on a process called simultaneous localization and mapping, or SLAM.
SLAM. Heard that term a lot. What is it exactly?
It's essentially how AMRs see and understand their surroundings. The initial step involves the robot being often manually driven around the facility. As it moves, it uses its sensors, usually LiDAR, to systematically scan its surroundings and generate a comprehensive, typically three-dimensional map of the space.
So it builds its own digital blueprint of the warehouse or factory.
Precisely. This map, this detailed digital representation of the workspace, is then stored in the robot's memory.
Okay, it has the map. Then what? How does it use it during operation?
During actual operation, the AMR continuously gathers real-time sensory data from its environment using its various sensors. This live data is then constantly compared to that stored map.
Ah, like constantly checking its position against the blueprint.
Exactly. This comparison allows the robot to assess its current position with pinpoint accuracy. That's the localization part of SLAM. And simultaneously, it allows it to detect any changes in the layout or any unexpected obstacles that weren't on the original map. That's the mapping part, constantly updating its understanding.
So the map isn't static. It can be updated.
It's dynamic. And the map can be further enhanced with additional contextual information. You can program in things like keep-out zones where the robot should never go, or speed reduction areas for safety in busy corridors, or precise docking station locations for charging or material transfers.
Giving it rules of the road, basically.
Exactly. This provides crucial dynamic awareness that goes beyond just its immediate physical surroundings.
But you mentioned sensors. No single sensor is perfect on its own, right? The real power comes from combining them.
Absolutely critical point.
Yeah.
The true power, the robustness, comes from diverse sensors working in concert. This is the concept of sensor fusion.
Sensor fusion sounds complex.
It is, but the idea is straightforward. It's the AMR's sophisticated eyes and ears, combining inputs for a better overall picture. Sensor fusion is fundamental because each sensor type has inherent strengths and weaknesses.
Like what kind of sensors are we talking about?
Key sensors typically include things like industrial vision time of flight or tool-focused cameras. They measure depth very accurately by calculating the time it takes for light pulses to bounce back.
Okay, TOF cameras for depth.
Then you have radar, which is excellent for detecting objects even through challenging conditions like fog, dust, or rain where cameras might struggle.
Radar is good in bad weather.
Exactly. LiDAR scanners, which use pulsed lasers to create very precise, detailed 3D maps of the surroundings. Very common in AMRs.
LiDAR for mapping.
3D depth sensing cameras, which provide intricate spatial understanding, good for close-range maneuvering and object recognition. And of course, standard RGB cameras, like the ones in your phone, for visual information, reading signs or barcodes, and general object recognition.
So it's using all of these different inputs together.
Yes, the data from all these different streams is then intelligently fused, combined, and filtered to create a single, coherent, and highly reliable understanding of the environment.
And our sources really emphasize the importance of inertial measurement units, IMUs, as being critical for precise positioning, especially when maybe the visual environment is tricky.
IMUs are absolutely indispensable. They provide foundational motion data that's independent of external visual features. An IMU typically integrates three types of sensors: accelerometers, gyroscopes, and sometimes magnetometers.
Okay, what do they each do?
Accelerometers measure linear acceleration speeding up, slowing down. Gyroscopes measure angular velocity turning, tilting, and magnetometers measure magnetic field orientation, essentially acting like a compass.
So it knows how it's moving and rotating internally.
Precisely. Together, they provide high-fidelity positional output, often at very high data rates, like 4,000 times per second raw data. This significantly enhances reliability, especially in dynamic environments where other sensors might get confused or lose track temporarily.
And you mentioned environments where SLAM might struggle.
Yes, IMUs are particularly vital in what we call feature-sparse environments. Imagine a very long, uniform warehouse corridor with identical walls, or a wide-open production floor with very few distinct visual landmarks.
Where LiDAR or cameras might not see enough unique features to know where they are.
Exactly. In those scenarios, SLAM can struggle to localize effectively. But the IMU provides that critical heading and orientation information internally, preventing the robot from getting lost or disoriented. It acts as a reliable internal compass and motion sensor.
So it fills in the gaps when the external sensors are having trouble.
Perfectly put. And unlike visual sensors like cameras, IMUs are remarkably robust across diverse environmental conditions. They don't care about ambient light levels or the presence of dust, fog, or rain. They aren't confused by reflective surfaces that can trick optical sensors. They can even tolerate a degree of dynamic obstacles moving around them and some electromagnetic interference. They provide consistent performance.
That robustness sounds key for industrial settings, and they help with slopes, too.
Yes, that's another often overlooked challenge. Traditional 2D SLAM systems, the simpler ones, often misinterpret changes in elevation like ramps or slopes as vertical walls, or they just struggle to maintain accurate localization when going up or down.
They think the ramp is a wall.
Sometimes, yes, or they lose track of their z-height. But IMUs, because they measure tilt and orientation in 3D space, can extract precise gradient information. This allows the robot to effectively understand and negotiate these changes in terrain with confidence.
Okay, so IMUs are crucial. What about wheel odometry? That sounds simpler.
It is simpler, but still important. Wheel odometry uses position encoders, sensors directly attached to the robot's wheels or motors, to provide data on how much the wheels have rotated. It's like the odometer in your car, but more precise. It gives the robot constant feedback on how far and in what direction it thinks it's moved based on wheel rotation.
But wheels can slip, right? So it's not perfectly accurate on its own.
Exactly. Wheel slippage is a common issue, especially on smooth or dirty floors. That's why odometry is almost always used in combination with other sensors like LiDAR and IMUs through that sensor fusion process we talked about.
Right, bring it all together.
All this disparate data from LiDAR, cameras, IMUs, wheel encoders gets combined. Sophisticated algorithms, often things like the extended Kalman filter, EKF, which is a mathematical technique for estimation, are used. These algorithms often run within a larger framework like the Robot Operating System, or ROS.
ROF. Okay, we'll come back to that. But the Kalman filter fuses the data.
Yes, it intelligently combines the measurements from all the sensors, weighting them based on their expected accuracy and uncertainty to produce a much more precise and reliable estimate of the robot's position, orientation, and velocity than any single sensor could provide. And it does this continuously, constantly refining the estimate and updating the map.
It's like a constant, super fast feedback loop. Always checking, always correcting.
Exactly. Ensuring the robot always knows, with high confidence, exactly where it is, where it's going, and what's around it, even in a chaotic and constantly changing industrial environment. This level of real-time, robust understanding is absolutely fundamental to achieving true, safe autonomy.
Okay, that covers the brain's sensing and understanding. Now, what about the nervous system? How do all these different parts inside the robot talk to each other? The wheel drives, the vision inputs, the IMU, the battery system, they all need to communicate, right? Quickly and reliably.
You're absolutely right. It's an intricate internal communication network. All these components need to transmit critical messages back and forth constantly for navigation, task execution, safety checks, everything.
So what kind of communication methods do they use inside the robot?
A typical AMR might actually employ multiple wired communication methods internally. Each protocol is often chosen for its specific strengths regarding speed, latency delay, robustness against noise, and suitability for the type of data being sent.
So not just one standard cable?
Often not. You might find protocols like Profibus, Profinet, EtherCAT, Ethernet IP. These are common industrial Ethernet standards known for real-time performance. You might also see simpler ones like UART or RS-485 for lower speed serial communication, CAN bus, which is common in automotive and robotics for reliable messaging, or maybe SPI for chip-to-chip communication.
Wow, that's a lot of different languages for one robot to speak just internally. It sounds complex to manage.
It can be. Each protocol serves a specific purpose, ensuring that high-speed motor commands get through instantly, while sensor data is relayed without delay and status updates are shared reliably. It's about optimizing that internal data flow for performance and reliability.
And our sources mentioned a newer protocol gaining traction, especially for sensor data, GMSL.
Yes, Gigabit Multimedia Serial Link, or GMSL, is becoming quite significant, particularly because it was initially developed for automotive advanced driver assistance systems, ADS, which have very similar high bandwidth sensing needs to AMRs.
What makes GMSL special?
Its main advantages are extremely high bandwidth. It can handle up to 6 gigabits per second and very low latency, all transmitted over a single, relatively simple and robust coaxial cable.
6 gigabits over one coax cable, that's a lot.
It is. This significantly simplifies the challenge of aggregating data from multiple high-bandwidth sensors, like high-resolution video cameras, LiDAR scanners, and radar units. And importantly, GMSL can often transfer power and control signals over that same single cable.
Power, control, and massive data on one cable. That must simplify the robot's design.
Hugely. It streamlines the internal wiring, reduces the number of connectors, which are potential points of failure, saves space and weight, and generally enhances the overall reliability of the sensor system. It's a big step forward for complex sensor integration.
Okay, so that's internal wired communication, but AMRs also need to talk to the outside world, right? To the base station, maybe other robots.
Absolutely essential. Beyond the internal wired network, robust wireless communication is critical. Robots need to interact seamlessly with a central fleet management system or base station to receive new missions, report their status and position, download map updates, and crucially, coordinate effectively with other robots in the fleet.
Coordination is key, especially if you have dozens or hundreds of robots.
Exactly. This wireless link ensures seamless coordination throughout a facility, preventing collisions between robots and optimizing overall traffic flow.
And all of this communication, wired and wireless, needs to happen almost instantly, doesn't it? Real-time performance is critical.
Not just a preference, it's an absolute necessity for mobile robot operations, especially for things like instantaneous obstacle avoidance and reacting safely to dynamic changes in the environment. Even slight delays in communication, whether internal or external, could lead to collisions, inefficiencies, or significant disruptions in the workflow. The margin for error is incredibly small in these fast-paced industrial settings.
Okay, nervous system covered. Let's move to the muscles of the AMR, the intelligent motion control. How do they actually move around so efficiently and precisely?
Efficient movement is absolutely fundamental to AMR architecture, especially, as you pointed out earlier, because they're typically battery-operated. Every bit of energy counts.
Right, battery life is king.
So smarter, more efficient motor controllers directly translate to reduced energy waste. Less energy wasted means longer operational time between charges, which maximizes the robot's uptime and productivity.
Designing these motion systems must involve some serious, detailed engineering calculations, right?
Oh, absolutely. Calculating the required motor specifications is quite involved. Engineers need to consider a whole host of variables: the total mass of the vehicle itself, the maximum payload it's expected to carry, the diameter and mass of the wheels, the specific type of drive
So
system.
drive type, like two-wheel drive versus something else.
Exactly. Is it a differential drive, common with two powered wheels? Or perhaps an omnidirectional drive using special wheels like mecanum wheels, allowing it to move sideways or rotate in place.
Mm-hmm.
The number of wheels matters, the rolling friction of the surface it operates on, the desired maximum and minimum speeds, the overall system efficiency, and of course built-in safety factors.
That's a lot of factors just to pick the right motors.
And then you get into the actuator requirements, the motors themselves. This involves precise calculations of the system's inertia, the torque needed for acceleration torque, and the torque needed to overcome friction and inclines, load torque. Adding those together gives you the total peak torque the motors need to provide for smooth, reliable, and efficient movement under all expected conditions.
And how are these motors controlled so precisely? The sources mention something called field-oriented control, FOC.
Yes, FOC is highlighted as a highly efficient and precise method, particularly for controlling brushless DC, BLDC motors, which are very common in AMRs due to their efficiency and longevity.
What makes FOC so good?
Think about controlling an electric motor. Simpler methods just switch the power on and off to different windings. FOC is much more sophisticated. It uses sensor feedback, often Hall sensors or encoders, and complex algorithms to precisely control the magnetic field inside the motor in real time.
Controlling magnetic field directly.
Yes, by independently controlling the torque-producing and flux-producing components of the stator current, FOC allows for incredibly smooth rotation, very precise torque control even at low speeds, rapid dynamic response, and, crucially for battery life, significantly higher energy efficiency compared to simpler control methods. It wastes much less energy as heat.
So smoother, more precise, and more efficient. Sounds ideal for robots.
It really is.
Yeah.
And there are dedicated hardware solutions available now that simplify implementing FOC. For example, the sources mention Analog Devices' TMCM 2611 AGV module, which integrates hardware-based FOC specifically for AGVMR applications. These modules handle the complex calculations efficiently and offer flexible communication protocols and support for various feedback sensors, making it easier for robot designers to achieve that precise and efficient motion control.
So it's not just about getting the robot to move from A to B, but ensuring it does so with maximum precision and minimum energy consumption to preserve that precious battery life.
Exactly. Every joule counts.
Which brings us neatly to the final core component, the lifeblood of the AMR, the battery management system, or BMS. In these fast-paced automated environments, where, as we've said, every minute of downtime costs money, meticulous control over the battery seems absolutely crucial for continuous operation.
It is absolutely mission critical. A sophisticated battery management system is essentially the guardian of the battery pack. Its job is to constantly monitor and control a whole host of critical parameters to ensure the battery operates safely, efficiently, and lasts as long as possible.
What kind of parameters does a BMS track?
Key metrics include the state of charge, so NSE, which is like the fuel gauge telling you how much energy is left, the depth of discharge, DOD, indicating how deeply the battery has been depleted during use, the state of health, so NAC, which is a crucial measure of the battery's overall condition and remaining lifespan, tracking degradation over time. Plus, it constantly monitors cell temperatures, voltage levels of individual cells, and the current flowing in and out.
That's a lot of data just about the battery. Why is all that needed?
All this data is used by the BMS algorithms to optimize the battery's performance and significantly extend its lifespan. It prevents damage from operating outside safe limits. The choice of battery chemistry is also important here. Lithium-ion, Li-ion batteries are now overwhelmingly preferred for AMRs compared to older lead-acid types.
Why Li-ion? What are the advantages?
Li-ion offers several key benefits: much higher energy density, meaning you get more power in a smaller, lighter package. They can be charged much faster, reducing downtime. And they generally have a significantly longer cycle life, meaning they can handle more charge-discharge cycles before needing replacement.
But Li-ion batteries also have a reputation for needing careful management, right? They can be sensitive.
You're absolutely right. They are powerful, but require incredibly precise monitoring and control. Unlike lead acid, their voltage curve is flatter, meaning small changes in voltage can represent large changes in charge state. Even tiny voltage measurement errors down to the millivolt level across the individual cells within a pack can impact the accuracy of the cell calculation, affect overall efficiency, potentially lead to imbalances between cells, shorten the battery's lifespan, and in the worst-case scenarios, pose safety risks like overheating or thermal runaway if not managed properly.
So the BMS is a really critical safety role, too.
A huge safety rule. An efficient BMS mitigates these risks by providing extremely accurate cell voltage measurements, implementing sophisticated cell balancing strategies during charging to keep all cells at the same level, enabling synchronous current and voltage measurements for precise power calculations, and facilitating very fast overcurrent detection to protect against short circuits.
So it's constantly watching and adjusting to keep the battery safe and healthy.
Exactly. This comprehensive management significantly reduces the risk of common battery issues, like overcharging over discharging, which damages Li-ion cells, and overheating. This directly impacts the robot's operational efficiency, its safety profile, and ultimately its total cost of ownership by maximizing battery life.
And there's a sustainability angle here, too, which feels increasingly important. Better battery management means longer life.
Which means fewer batteries need to be manufactured and disposed of. Efficient battery management directly extends battery lifespan, reducing the frequency of costly replacements and minimizing the environmental impact associated with battery production and end-of-life disposal. It aligns perfectly with the broader goals of the clean energy transition and sustainable operations. It's a clear win-win, both economically and environmentally.
Okay, we've really gone deep into the intricate internal workings, the brain, nerves, muscles, lifeblood. Now let's zoom back out. How are these sophisticated machines actually brought into a real-world factory or warehouse and made to work effectively? Strategic deployment and seamless integration seem absolutely critical to actually getting the benefits we've been talking about.
They are absolutely critical. You can have the best robot technology in the world, but if it's not deployed thoughtfully and integrated properly into the existing environment and workflows, you won't realize its full potential.
So how does a typical deployment actually happen? Our sources laid out a kind of standard process, usually involving about 6 stages.
That's right. It typically starts, logically enough, with analyzing the existing human operations. This involves a deep dive into the current workflows, observing how people currently move materials, what paths they take, where the bottlenecks are, and identifying which specific tasks are repetitive, inefficient, perhaps physically strenuous or dangerous. These become the prime candidates for automation.
So step 1 is really understanding the as-is state in detail. What's next?
The second stage is selecting the optimal AMRs and any accompanying components like charging stations or maybe specific top modules for the robots tailored to your specific warehouse or factory's performance needs. This isn't just about picking any robot. It's about choosing the right type, size, payload capacity, navigation capabilities, and battery life to perfectly match the tasks you identified in stage 1.
Makes sense. Choose the right tool for the job. Stage 3.
Stage 3 is engineering the combined AM-Human workflows. This is a really crucial collaborative step. It's where you thoughtfully design the new processes, deciding the best way to integrate the humans and the AMRs so they can work together seamlessly and effectively. Who does what? How do handoffs occur? What are the interaction points?
So you design the new dance between people and robots, and then you deploy.
Not quite yet. Before you even think about physical deployment, there's a vital fourth step that's often underestimated but incredibly valuable. Simulation.
Simulation.
Using a digital twin.
Exactly. You create a digital twin, a highly accurate, dynamic virtual model of your real-life warehouse or factory. This model includes the layout, typical traffic patterns, maybe even the physics of the robots and the loads they carry.
And you run the robots in this virtual world first.
Precisely. This digital twin is used to test various scenarios for the planned AMR implementation, using real-life data where possible. It's incredibly smart because it allows you to iron out kinks and prevent potentially costly or dangerous issues before a single physical robot hits the floor. Like what kind of issues?
You can test if robots might tip over when cornering too fast with a certain load, identify potential traffic jam points in narrow aisles, Ensure safety protocols work correctly. Verify that robots can reach charging stations reliably. By modeling the robot logic and physics, you can ensure safety and optimize efficiency long before making substantial physical investments or disrupting operations.
And you can test different fleet sizes or strategies.
Yes, large-scale simulations allow you to tweak fleet management strategies, determine the optimal number of robots needed to meet throughput targets, and fine-tune how robots cooperate and prioritize tasks for maximum overall efficiency. It's all about mitigating risk and optimizing performance in a safe, virtual environment first.
Okay, simulation sounds essential. Then comes deployment.
Yes. Only once the simulations confirm that the planned workflows are safe, efficient, and meet the performance goals do you move to the fifth stage, the actual deployment. This involves physically implementing those new simulation-validated AMR workflows, configuring the robots on site, integrating them with your Wi-Fi network, and potentially other systems like warehouse management systems, WMS, and getting everything up and running.
And stage 6, is it just run?
Stage 6 is long-term support and continuous changes. Deployment isn't a one-and-done event. This stage involves providing ongoing hardware maintenance and software updates, which often include new features or performance improvements, gathering real-time feedback and performance data, and being prepared to refine and adapt the workflows over time to ensure sustained efficiency and scalability as your business needs inevitably evolve. It's an iterative life cycle.
That sounds like a truly thorough, planned, and iterative approach. So beyond that initial deployment process, what are some ongoing best practices for ensuring seamless integration and really maximizing the value of these AMRs once they're operational day to day?
Great question. First and foremost, building on stage 1, are thorough site assessments, not just initially, but perhaps periodically.
Yeah.
You need a continuous, detailed understanding of the facility layout, potential pathways, fixed and temporary obstacles, areas of high human or forklift traffic. You need to constantly evaluate current workflows, map out material flow, and always be looking for new opportunities for automation or optimization. Complacency is the enemy here.
So always be assessing. What else?
Workflow optimization is key. This means meticulously mapping the entire production or logistics process, identifying bottlenecks, and really leveraging the AMR's flexible navigation systems. Program routes intelligently to minimize travel time, avoid known congestion points, perhaps schedule certain tasks for off-peak hours. Many advanced fleet management systems now include sophisticated load balancing features to distribute tasks evenly across multiple robots, preventing situations where one robot is overworked while others sit idle, and ensuring smooth overall flow.
And safety and compliance must remain absolutely top of mind, especially with robots and people sharing the floor.
Unquestionably. You absolutely must conduct comprehensive risk assessments on an ongoing basis, not just at the start. Identify any new potential hazards related to AMR operation as things change, and update your mitigation strategies accordingly. Implementing and consistently reinforcing robust safety protocols is non-negotiable.
Like what specifically?
Clear emergency stop mechanisms easily accessible to staff, ensuring the advanced collision avoidance systems are always functioning correctly, clearly marking designated AMR pathways, and maybe creating pedestrian-only zones, and continuous training for staff on how to interact safely with the robots.
And adhering to standards is crucial. You mentioned ISO 36914 earlier.
Adherence to industry standards and regulatory guidelines is not just best practice. It's often legally required and essential for insurance and liability. That EU Machinery Regulation 2023-1230 coming into effect in January 2027 is a big one. It explicitly defines autonomous mobile machinery and mandates product conformity with harmonized safety standards. Type A fundamental, Type B generic safety like emergency stops, and Type C machine-specific standards.
So manufacturers and users both need to be compliant.
Absolutely. This includes implementing appropriate protective measures, like those electrosensitive protective equipment, ESPE, devices. We discuss things like safety-rated 2D laser scanners or 3D time-of-flight sensors, specifically designed for reliable person detection around the robot. The braking systems must activate immediately and reliably upon detecting excessive speed or a person in the safety zone, and they often need to meet demanding functional safety levels, like Performance Level D, PLD, according to ISO 13849-1.
PLD sounds serious.
It is. It requires highly reliable safety functions with very low probability of dangerous failure. Beyond the hardware, maintaining diligent documentation of safety procedures and incidents, conducting regular safety audits, providing continuous safety training for all personnel, not just operators, and establishing clear, open communication channels for reporting any safety concerns are all essential components of a safe, compliant, and ultimately successful AMR operation. Safety has to be woven into the culture.
It's clear that successful AMR integration is way more than just the robot itself. It's this whole complex ecosystem around it. So, beyond the robot and safety, how do companies really maximize that ROI we talked about?
A key strategy is deep integration with existing enterprise systems. AMR shouldn't operate in an information silo. They need to be seamlessly connected with your core business systems, like your enterprise resource planning, ERP system, your manufacturing execution system, MES if you're in production, or your warehouse management system, WMS.
Why is that integration so important?
It ensures seamless data flow in both directions. The WMS can send orders directly to the AMR fleet management system, and the AMRs can report task completion, inventory movements, or even potential issues back to the WMS or MES in real time. This enables real-time monitoring of operations, provides valuable data for analysis, and allows for more proactive decision-making and dynamic adjustments.
Data-driven decisions.
Exactly. And that ties into the next point.
Yeah.
The focus must be on continuous improvement. Don't just deploy and forget. Regularly review key performance metrics, throughput rates, robot uptime, average travel times, task completion accuracy, battery usage patterns. Use that data to identify areas for improvement and make data-driven adjustments to robot routes, task assignments, maybe even workflow designs. This iterative optimization cycle is vital for squeezing out ongoing efficiency gains and truly maximizing that ROI over the long term.
And we absolutely cannot forget the people in this equation. Training and development for the existing workforce, it seems not just beneficial, but essential for making this transition work smoothly and successfully.
You're completely right. It's arguably one of the most critical success factors. Familiarizing teams with the operational nuances of the AMRs, how they move, how to interact with them, what their lights or signals mean, and critically reinforcing all the safety protocols through hands-on training sessions and easily accessible e-learning modules is absolutely paramount.
So initial training is key, but what about ongoing?
Beyond the initial onboarding, fostering a culture of continuous improvement and learning is vital. This could involve regular workshops, making online resources readily available, establishing clear feedback loops where employees can share observations or suggestions about the robots. It's about empowering the employees. This proactive approach helps make the transition much smoother by clearly emphasizing the benefits of increased productivity, yes, but also reduced manual strain and enhanced safety. It builds confidence in the new technologies and provides ongoing support as job roles inevitably evolve alongside the automation.
And the sources highlighted some powerful examples of this impact on labor and training. You mentioned one earlier about a 3PL.
Yes, that case study was striking. A third-party logistics provider dramatically reduced their labor dependency on a specific manual, paper-based picking line from 22 associates down to just 9.
Wow, less than half the staff needed for the same or more output.
Exactly. And simultaneously, they increased the picking productivity on that line to an astounding 800 picks per hour.
800 picks per hour. How did the AMRs enable that?
By fundamentally changing the workflow. Instead of associates walking miles to pick items from shelves and transport them, the associates stayed in optimized zones, focusing purely on the picking task. The AMRs autonomously traveled to the picker, received the items, and then transported them to the packing or shipping area. It eliminated all that unproductive walking time and the physical strain of pushing heavy carts.
So the humans did the skilled picking, the robots did the less skilled travel.
Precisely. And what was also remarkable was that this massive efficiency gain was achieved with less than 1 hour of operator training required for the new AMR-supported process.
Less than an hour. That's incredible compared to learning a whole warehouse layout.
Because the new operators simply needed to learn how to interact with the robot at their fixed station. Maybe scan a barcode, place items in the robot's bin. They didn't need to memorize complex warehouse layouts or optimal pick routes. The system managed the complexity. It streamlined the human task, de-skilled the movement aspect, making the human role much more efficient, focused, and less physically demanding. It's a profound demonstration of efficiency gains and accelerating time to expertise.
That's truly a powerful example. Okay, so we've got deployment and human integration covered, but you mentioned earlier that AMRs rarely operate in isolation. They have to interact with other automation in the facility, interoperability, and managing a whole fleet. That sounds like a massive challenge, especially if you have robots from different vendors.
It is one of the biggest challenges today and a crucial area of ongoing development and standardization efforts. You're right. AMRs are rarely the only automation system in a modern, complex facility. They must communicate and coordinate seamlessly with a whole ecosystem of other equipment.
Like what?
Fixed hardware like elevators, AMRs need to call and ride elevators. Overhead cameras used for monitoring or traffic management. Various sensors embedded in the facility. Conveyor belts. Automated sorting machines. Doors that need to open automatically for them. The list goes on.
So they need to talk to the building itself in a way.
In a way, yes. And moreover, they need to integrate smoothly with those higher-level software systems we discussed, ERP, MES, WMS, to get tasks and report status. A truly holistic approach to automation for the entire facility is crucial. You need to devise systems where all the automation equipment, regardless of type or vendor, functions as a cohesive, single, intelligently managed fleet.
A single fleet, even with different types of robots from different companies, how is that possible?
This requires sophisticated heterogeneous traffic management systems. These are software platforms designed to control and coordinate all mobile robots in the facility, irrespective of their manufacturer. They use standardized communication protocols, like VDA 5050 in Europe is emerging for this.
VDA 5050.
It's a standard interface specification, aiming to allow different AGVs and AMRs to communicate with a master control system using common messages. These fleet managers gather real-time data from all connected robots, their precise location, their current battery level, their intended destinations, their requests to enter shared zones like intersections or elevator lobbies.
And what does the fleet manager do with all that data?
Based on all this real-time information, the fleet manager dynamically optimizes paths for all robots, assigns priorities, reserves pathways, manages traffic flow at intersections, and orchestrates movements to minimize overall transit times, prevent deadlocks, and avoid collisions across the entire robotic workforce.
So it really is like a central air traffic control system for the ground, making sure everything runs smoothly and safely without robots crashing into each other or getting stuck.
That's an excellent analogy.
Mm.
And it's absolutely essential for achieving efficiency and safety when you have a large, diverse fleet of autonomous vehicles operating in a shared space.
This all sounds like it relies incredibly heavily on extremely sophisticated software at its core. The robots themselves, the fleet managers.
It absolutely does. Software is the intelligence, the glue holding it all together. Let's delve a bit into the power of software, specifically mentioning the robot operating system, ROS again, and the powerful algorithms that actually bring this autonomy to life.
Okay, ROS. You mentioned it earlier. It's not really an operating system like Windows or Linux.
No, not in the traditional sense. ROS is better described as a flexible robotics middleware. It provides a robust collection of software libraries, development tools, and conventions that significantly simplify the task of creating complex robot behaviors.
How does it simplify things?
It offers a standardized message-passing framework for communication between different software modules running on the robot or even across multiple computers. This allows for highly modular and scalable development, where different functionalities like sensor drivers, localization algorithms, navigation planners, motor controllers can be developed, tested, and updated independently as self-contained units called nodes.
So ROS provides the plumbing, the communication structure connecting these different software pieces, these nodes.
Exactly. You might have a node that's just responsible for publishing data from the LiDAR sensor. Another node takes that data and runs the SLAM algorithm. A third node handles motor control. A fourth node takes the desired goal and plans a path. They communicate through standardized ROS topics, which are like named broadcast channels for data or services, which work more like request-response function calls.
So you could have, say, an IMU driver node, a LiDAR driver node, a motor control node, a localization algorithm node, a collision detection node, a high-level navigation application node, all running and talking to each other via ROS.
Precisely. And this modularity is incredibly powerful. It allows developers to easily integrate new sensors or add new functionalities simply by creating or incorporating new nodes without needing to rewrite the entire system from scratch. It makes robots incredibly extensible and adaptable to new tasks or evolving hardware. ROS has really accelerated innovation in the robotics field because it fosters code reuse and collaboration.
Okay, so ROS provides the framework, but the actual intelligence, the decision-making, that comes from the algorithms running inside those nodes, right?
Absolutely. The algorithms are the core of the autonomy, the brain power that processes the sensor data and makes intelligent decisions. They leverage the hardware capabilities we discussed earlier.
What kind of algorithms are we talking about? Can we break them down?
Broadly, they fall into two critical categories: sensing algorithms and actuating algorithms.
Sensing and acting. Makes sense. What do sensing algorithms do?
Sensing algorithms are all about enabling the robot to perceive and interpret its environment. This includes technologies we've already touched on, like SLAM for localization and mapping. It also includes point cloud processing algorithms for analyzing the 3D data coming from LiDAR or depth cameras to understand shapes and distances.
Okay, what else?
Advanced object detection and recognition algorithms, often using AI and machine learning, allow the robot to identify specific things in its environment, like recognizing a person, a forklift, a pallet, or specific types of obstacles. Sensor fusion algorithms, like the Kalman filter we mentioned, are crucial sensing algorithms for combining data from multiple sensors into a single, more accurate state estimate.
Mm-hmm.
Attitude and heading reference systems, AHRS, are algorithms, often heavily reliant on IMU data that provide critical orientation information, roll, pitch, yaw. And increasingly important are human-robot interaction, HRI algorithms, which are emerging to allow robots to better understand human presence, gestures, or even predict human intent for safer and more intuitive collaboration.
Wow, okay. That's a lot going on just in sensing. And actuating algorithms, they control the movement.
Precisely. These are the control algorithms that translate the robot's understanding of the world and its desired goal into precise commands for the motors and actuators. They dictate how the robot moves.
What are some examples?
Common ones include proportional integral derivative, PID, control, which is a classic feedback control loop widely used for things like maintaining a desired speed or following a specific path accurately. More advanced techniques like model predictive control, MPC, are increasingly used. MPC uses a model of the robot's dynamics to predict how it will move in the near future and optimizes control actions over that time horizon to achieve goals smoothly and efficiently while respecting constraints like maximum speed or acceleration. And then there are trajectory generation and path planning algorithms like A-star or RRT, rapidly exploring random trees, which compute smooth, efficient, and crucially collision-free paths for the robot to follow from its current location to its destination, often needing to replan dynamically as the environment changes.
So it's this constant interplay. Sensing algorithms figure out what's going on, and actuating algorithms figure out how to move safely and efficiently based on that understanding.
Exactly. These algorithms, leveraging the robust hardware output from sensors and the power of processors, enable AMRs to process vast amounts of information in real time, detect obstacles, make intelligent decisions dynamically, and adapt their behavior instantly to the complexities of ever-changing, real-world industrial environments.
Yeah.
They are the intelligence that truly orchestrates the robot's brain, nerves, and muscles to achieve autonomous operation.
We've focused heavily, and rightly so, on manufacturing and warehousing logistics. That's clearly a massive area for AMRs. But you hinted earlier that they're moving beyond just logistics. Where else are these advanced mobile robots starting to make an impact, perhaps in applications we might not typically associate them with?
This is where we really see the incredible versatility and, frankly, the untapped potential of AMRs starting to shine. One major area is industrial surveillance and maintenance. This is actually a rapidly growing market in its own right, expanding by roughly 20% annually.
20% growth. Why such demand there?
Because traditionally, tasks like routine security patrolling of large sites, continuous monitoring of critical equipment or infrastructure, and rapid incident response have relied heavily on human personnel. But these jobs face significant challenges. It's often difficult to find and retain qualified people willing to do repetitive patrols, especially outdoors in adverse weather conditions, or work complex, round-the-clock schedules. Plus, some monitoring tasks involve inherent risks.
So AMRs are stepping in to fill those gaps, complementing human teams in security and maintenance roles?
Exactly. They're not necessarily replacing security guards entirely, but augmenting them, offering several profound benefits. First, increased efficiency and consistency. AMRs can perform consistent, methodical, and accurate patrolling of large, often remote or potentially hazardous areas 24/7, regardless of weather conditions or time of day. Something that's very challenging and costly to achieve with human teams alone.
Tireless patrolling.
Tireless and objective. Second, and really crucial, increased occupational safety. By taking over routine inspections or patrols in potentially hazardous situations, think areas with harmful chemicals, extreme temperatures, high voltage equipment, confined spaces, AMRs significantly reduce human personnel exposure to risks.
Getting people out of harm's way.
Precisely. And third, enhanced data collection and reporting. AMRs excel at systematically recording precise data during their patrols. High-resolution images, video footage, thermal readings, acoustic data. This information can be invaluable for security investigations, fulfilling legal evidence requirements, tracking maintenance needs, or continuously improving safety and security protocols based on empirical, objective data, not just subjective observation.
That makes a lot of sense. Can you give some specific real-world examples of AMRs taking on these specialized roles?
Sure. For quality inspection, mobile robots, or particularly the mobile manipulators we'll discuss later, equipped with advanced AI vision systems, can perform exhaustive, highly detailed quality controls of machinery, individual parts coming off a line, or finished products. They can spot tiny defects or inconsistencies that a human inspector might miss after hours of repetitive visual checks.
Okay, automated quality control. What else?
For perimeter inspection, AMRs can continuously monitor fences, pipelines, or other critical infrastructure for security breaches, damage, or anomalies. They minimize the potential for human error or fatigue in monotonous patrol tasks and provide reliable, time-stamped, geotagged data records of their observations.
So, like automated watchmen for large facilities.
Essentially, yes. In the energy industry, we're seeing robots being deployed to patrol high-voltage areas in electrical substations. The sources mention Robotnik deploying robots at EDP, a major utility. These robots use thermal cameras and other sensors to detect irregularities like overheating components on transformers or circuit breakers or abnormal sounds, transmitting real-time alerts to operators. This allows for proactive maintenance, preventing potential equipment failures, costly outages, or dangerous safety incidents.
Wow, patrolling live substations. That's definitely a job you'd rather a robot did.
Absolutely. And their application extends further into critical infrastructure monitoring. Think about inspecting aging civil infrastructure like bridges, tunnels, dams, or roads for signs of wear, cracks, or potential structural issues. AMRs can access hard-to-reach areas and gather detailed sensor data for preventive maintenance planning and ensuring public safety. There are several large research projects, like those under the EU's Horizon Europe program, focusing specifically on this, names like piloting for refineries and bridges, Heron for road maintenance inspection, and InRobot, looking at using robots with haptic feedback for inspecting hazardous areas.
Haptic feedback, like the robot can feel the surface.
Potentially, yes, or transmit tactile information back to a remote operator. The technology is pushing boundaries. And then you have highly specialized surveillance robots being developed, like the RB Watcher mentioned in the sources.
RB Watcher. Tell us more about that one. It sounds particularly advanced. What can it do?
The RB Watcher is designed for really versatile surveillance operations. It's capable of navigating autonomously both indoors, using sophisticated 3D SLAM, and outdoors, using GPS for positioning. It's equipped with advanced obstacle avoidance capabilities, of course, and it can report real-time data, video feeds, and alerts directly back to a central security control center.
What makes it so specialized for surveillance? It's sensors.
Exactly. What makes it particularly powerful is its integrated suite of specialized sensors and the software that processes their data. It incorporates advanced image recognition software, often AI-powered, to identify specific objects or anomalies, detect if a person is in a restricted area, recognize specific vehicle types, maybe even spot abandoned packages. It has a depth camera for precise spatial understanding and navigation in complex areas, motion sensors for detecting movement, a thermal camera for identifying heat signatures, incredibly useful for detecting people in darkness, potential fires, or overheating equipment.
Thermal vision is powerful.
Very. It also features a bispectral pan-tilt zoom, PTZ camera, which combines both visual and thermal imaging capabilities in a maneuverable camera head, allowing for high-resolution surveillance day or night and the ability to zoom in on suspicious activity. And it even includes microphones for detecting unusual sounds and speakers for broadcasting warnings or enabling two-way communication with a remote operator.
So it's like a mobile, multi-sensor security platform. It can see, hear, sense heat, recognize objects.
Pretty much, this comprehensive sensor array allows it to autonomously detect people, potential fires, unauthorized vehicles, or other suspicious objects with incredible precision and reliability, demonstrating a significant expansion of AMR capabilities far beyond just moving materials in a warehouse. It's intelligence and sensing on wheels, deployed for safety and security.
This expansion of capabilities, especially into areas like surveillance and maintenance, really starts to solidify that vision of Industry 5.0 that you mentioned earlier, the focus on the human element, the blending of workforces. It feels like a fundamental shift in manufacturing and industrial philosophy, moving beyond just connecting machines to truly optimizing how humans and robots work together.
This is a absolutely crucial evolution, and it builds directly upon the foundations laid by Industry 4.0. While Industry 4.0 was primarily focused on connectivity, connecting factories, machines, and systems, enabling machines to communicate and, to some extent, govern themselves through pervasive interconnection, machine learning, and real-time data.
Making the smart factory.
Exactly. Industry 5.0 takes that a significant step further. It shifts the focus to emphasize the collaboration and optimization of people and automation working in concert. Its core principles revolve around using technology to support and augment staff rather than simply replacing them. The goal is to achieve an ideal, symbiotic balance between human skills and technological efficiency and productivity.
So it's not the dystopian vision of robots taking over all the jobs.
Not at all, according to the Industry 5.0 philosophy. It's about robots helping us do our jobs better, more safely, more efficiently, and perhaps even more engagingly. That's the real vision behind the term blended workforce.
The blended workforce, I like that term.
It captures it well. The future of work, certainly in manufacturing and logistics, but likely in many other sectors too, will increasingly be built on the deliberate and thoughtful optimization of people and robots operating side by side. This intelligent collaboration leads to those faster, more efficient, and more cost-effective workflows we've discussed, where the whole is truly greater than the sum of its parts. It's about strategically leveraging the unique strengths of both human ingenuity, creativity, and adaptability, alongside robotic precision, endurance, and strength.
This naturally implies a significant reconfiguring of job roles and responsibilities within organizations adopting this model.
It absolutely does. Companies and their managers need to proactively recognize and leverage the distinct strengths of both their human workers and their robotic systems. It requires a strategic shift in thinking about task allocation. Managers can, and should, look to shift those repetitive, mundane, physically strenuous, or dangerous tasks. The constant heavy lifting, the miles of walking to retrieve inventory, the mind-numbing material movements over to the robots, where they excel.
Freeing up the humans for what?
For the tasks that genuinely require uniquely human skills. Critical thinking, complex problem-solving, creativity and innovation, nuanced decision-making, customer interaction, managing exceptions, and interpersonal communication and teamwork. This strategic reallocation doesn't just make operations more efficient, it profoundly empowers human workers. By freeing them from the triple D grind, it allows them to focus on more stimulating, engaging, and ultimately more valuable work. This can lead to significantly increased job satisfaction, higher levels of engagement, and a more dynamic and motivating work environment. People feel less like cogs in a machine and more like valued contributors using their higher-level skills.
And the safety aspect is huge here too.
Immense. Automation directly improves worker health and safety by substantially reducing the number of incidents and injuries related to manual handling, repetitive strain, or exposure to hazardous conditions. Reducing the dependency on manual, physically demanding work is a major benefit. In fact, our sources indicate that improving worker health and safety is a key driver for technology investment for 43% of manufacturers.
43%, so it's a major priority right up there with productivity and cost reduction.
Exactly. It demonstrates that companies see this not just as an efficiency play, but as a fundamental investment in their workforce's well-being.
That's a significant shift in focus. And it even extends, fascinatingly, to accelerating the time it takes for new employees to become proficient, to reach expertise. How do AMRs help with training?
It's a really interesting application. AMRs can actually function as incredibly effective real-time training aids for new hires or even existing workers learning new tasks.
How would that work in practice?
For instance, an AMR could be programmed to lead a new employee directly to specific workstations or inventory locations within a large, complex facility, essentially acting as a personal guide. They could display step-by-step instructions or checklists for a particular task right on an integrated screen. They could even provide on-demand information about special handling requirements for specific parts or materials when the worker scans an item.
So the robot becomes a mobile tutor or guide.
Precisely. This innovative approach can significantly reduce the learning curve and the overall training time required for new staff to become productive. This directly addresses a major challenge many companies face: finding and quickly onboarding experienced talent in a competitive labor market. It helps get new people up to speed faster and more effectively.
And that 3PL case study you mentioned earlier really drove this home, didn't it? Reducing labor dependency from 22 down to 9, increasing picks to 800 per hour. That all happened with less than an hour of training.
Yes, that specific example perfectly illustrates this synergy. Remember, they shifted from a highly manual, paper-based pick list process where workers needed extensive knowledge of the warehouse layout and spent most of their time walking.
Right.
By implementing AMRs to handle the transportation piece, the human role became much more focused and simpler. Stay in your zone, pick accurately when the robot arrives, place items in the bin. The robot and the system handle the complexity of navigation and task sequencing.
So the required skill set for the human operator changed and became easier to learn quickly.
Exactly. The training requirement plummeted to less than an hour because the new operators only needed to learn the simple interaction at their station, not the entire complex warehouse operation. It streamlined the process, dramatically boosted productivity by eliminating wasted travel time, and made the human role more efficient, less physically demanding, and much faster to train for. It's a perfect example of that blended workforce optimizing both human and robot contributions.
Okay, so we've covered the pressing need, the core distinctions between AMRs and AGVs, the incredibly intricate technology inside them, the strategic deployment, the expansion into new areas, and this profound human element shaping Industry 5.0. Looking ahead now, what's on the horizon for industrial mobile robotics? What are the top trends we should be watching for, say, in 2025 and beyond that will define the next chapter?
It's a field that's definitely not standing still. Based on the research, there are three major interconnected trends that are really poised to reshape the landscape significantly in the near future.
Okay, trend number one.
Trend one is a significant leap towards greater autonomy through artificial intelligence, AI. We're moving beyond robots that just follow complex pre-programmed rules to robots that can truly learn and adapt.
You mean machine learning, generative AI, that kind of thing?
Exactly. These AI techniques are creating what some are calling cognitive robots, machines that can genuinely learn from their experiences in the environment, make increasingly complex autonomous decisions in novel situations, adapt intelligently and proactively to constantly changing scenarios, and maybe even learn to reenact subtle human behaviors or movements, leading to much more natural and intuitive human-robot interaction.
So robots that aren't just executing instructions, but are actually thinking, learning, and becoming more like partners? That sounds like a huge jump.
It is. And it's being enabled by rapid advancements in hardware as well, particularly the increasing potential for powerful AI engines to run efficiently right on the robot itself, what we call intelligence at the edge. New ultra-low-power convolutional neural network, CNN accelerators, and similar AI-optimized chips allow complex AI models to run locally on the device.
Why is running AI locally so important?
It allows for much faster, more localized decision-making right on the robot, without the latency or potential unreliability of constantly needing to communicate with a central cloud server for every decision. This unlocks immense new efficiencies, faster reaction times, and greater robustness. And crucially, these AI advancements, better perception, better prediction, better decision-making, are making robots significantly safer and more predictable to integrate into diverse, dynamic human work environments. We're moving beyond simple collision avoidance to robots that can potentially understand human intent or anticipate actions for truly seamless collaboration.
Okay, smarter, more cognitive robots through AI. What's trend number two? You hinted at this earlier.
Trend two is the rise of mobile manipulator robots, or MoMAs. This sounds a bit sci-fi, but it's becoming very real.
Mobile manipulators. So, arms on wheels.
Essentially, yes. This next evolution in mobile robotics merges the inherent mobility and autonomous navigation capabilities of an AMR platform with the dexterity, precision, and manipulation capabilities of a mounted robotic arm, like the ones you see in factories today.
So combining the best of both worlds, moving and doing.
Precisely. This isn't just about moving materials from point A to point B anymore. It's about moving to point B and then performing a task that requires manipulation. MoMAs are set to bridge that critical gap between mobility and manipulation.
What kind of tasks do they do?
A huge range. They could potentially perform precise inspections using sensors on the arm, carry out delicate assembly tasks, pick items directly from shelves or bins, mobile picking, 10 machines, or even conduct complex maintenance procedures on equipment around a facility, potentially operating 24/7 using advanced sensors and cameras integrated onto the arm and the mobile base.
So they're not just bringing the tools or parts to the job, they could actually be the tool and do the job right there at the destination. That sounds like a profound game changer for maintenance, assembly, logistics.
It absolutely is. Imagine a MoMA autonomously navigating to a machine, using its arm to open a panel, performing a diagnostic check with a sensor, maybe even tightening a loose bolt, and then closing the panel and moving to the next task. The potential is enormous. Continued advancements in the underlying algorithms for sophisticated path planning for both the base and the arm, for enhanced obstacle detection in complex 3D workspaces, for advanced collision avoidance, considering the entire robot's geometry will continue to push the boundaries of MoMA capabilities, making them increasingly versatile and indispensable across a much wider range of industrial and even commercial applications.
Okay, AI-driven autonomy, mobile manipulators. What's the third big trend?
The third trend sounds perhaps the most futuristic, but the groundwork is being laid now. The concept of robot swarms.
Swarms, like bees or ants, but with robots.
Exactly that kind of concept. It's the idea of multiple, often smaller, potentially simpler and lower-cost mobile robots working together collaboratively and coordinately as a swarm or a collective.
How would that be different from just having a fleet of independent AMRs?
The key difference is the level of coordination and emergent behavior. A swarm represents a truly transformative approach, where the collective intelligence and action of the group allows them to accomplish far more complex or large-scale tasks than any single robot, even a large one, could achieve alone.
How would they work together?
They might work in parallel, for example, dozens of small robots simultaneously sorting packages in a distribution center, or mapping a large area much faster than one robot could. Or they might perform precise, choreographed handoffs, where tasks are seamlessly passed from one robot to another in a chain or sequence. The potential efficiency gains from this kind of distributed parallel operation can be exponential.
But getting dozens or hundreds of robots to work together like that must require incredible communication, right?
That is the absolute linchpin. The success of robot swarms relies critically on seamless, real-time, ultra-low latency communication among all robots within the swarm, and potentially with a central coordinator. Any lost messages, significant delays, or out-of-order information packets could instantly disrupt the entire coordinated operation, leading to collisions, inefficiencies, or task failures. The communication has to be near perfect.
So what's enabling this now? Are the communication technologies catching up?
Yes, the technological enablers are rapidly advancing to make large-scale swarm robotics feasible. We're seeing breakthroughs in communication protocols specifically designed for high-density, low-latency machine-to-machine M2M exchanges, like advancements in 5G and future 6G wireless technologies. We're seeing significant improvements in edge computing architectures that allow more processing locally within the swarm, reducing reliance on centralized control. And we're seeing that powerful merging of information technology IT networks and operational technology OT networks within facilities.
IT-OT convergence.
Exactly. This convergence is creating the robust, reliable, high-bandwidth, low-latency communication backbone necessary to unlock the immense potential of intelligent, coordinated robot swarms in real-world applications.
Wow. AI-driven autonomy, mobile manipulators doing tasks, and coordinated swarms. It really paints a picture of a dramatically different industrial future. This all points to an incredibly dynamic and rapidly evolving ecosystem, doesn't it?
It certainly does. These future robotic innovations will clearly demand even greater levels of system integration connecting robots, sensors, enterprise software, edge computing, cloud platforms, and require even closer collaboration between the robot developers, the component suppliers, the software providers, and their end-user customers to fully design, deploy, and leverage these advanced capabilities effectively. It's becoming much more about integrated solutions than just standalone robots.
And the market growth figures we touched on earlier really underscore the momentum here. They're just staggering.
They truly are almost hard to believe. The global market for AMRs, just in the segment of warehouses and distribution centers alone, is projected to skyrocket from around $1.8 billion recently to an astonishing $41.8 billion within the next 3 years.
From $1.8 billion to over $40 billion in just 3 years.
Yes. That's not just steady growth. It's a monumental explosion, a compound annual growth rate that's off the charts. It demonstrates the profound confidence the industry has in this technology's immediate and long-term transformative impact. We are genuinely on the cusp of, well, another industrial revolution, this one driven by intelligent mobile autonomy.
So after that deep dive, what does all of this mean for you, our listener? We've embarked on an incredible journey today, unpacking the world of autonomous mobile robots. We've explored their fundamental differences from older technologies like AGVs, which is crucial context. And we've delved into the intricate technological symphony, the sensors, the software, the controls that powers their perception, their movement, and their communication.
We've seen how they're not just about achieving incremental efficiency gains in familiar settings, like warehouses and factories, although they certainly do that incredibly well. They are truly reshaping the very definition of industrial work, significantly enhancing workplace safety and opening doors to entirely new and innovative applications, like using robots for critical industrial surveillance or proactive, predictive maintenance in ways we couldn't before.
And that significant shift towards a blended workforce, the core idea behind Industry 5.0, really highlights a future where human ingenuity and robotic precision aren't in opposition, but are locked in a powerful collaborative partnership, creating something together that's far greater, more resilient, and more impactful than either humans or machines could ever achieve alone.
We looked under the hood at those sophisticated brains, leveraging sensor fusion and SLAM to understand the world. We explored the complex nervous system of internal and external communication protocols that keep everything connected. We dissected the efficient muscles powered by intelligent motion control like FOC, and we understood the vital role of the lifeblood provided by advanced battery management systems that keep these robots running safely and efficiently for longer.
And we saw how strategic deployment isn't just about buying a robot, but involves meticulous planning, powerful simulation using digital twins, and an unwavering focus on human integration, training, and above all, safety. All these elements pave the way for maximizing that return on investment and ensuring long-term operational success.
The journey from AGVs to AI-powered MoMAs and swarms is accelerating, driven by converging technologies and pressing economic and labor needs.
So as the lines between the physical world of industry and the digital world of data and AI continue to blur, and as the capabilities of these autonomous systems grow almost exponentially year after year, here's a final thought to leave you with.
Consider your own environment, whether it's your workplace, your industry, or even just the broader community around you. What tasks that are currently repetitive, perhaps dangerous, maybe just inefficient, or even simply mundane, could be completely reimagined through the lens of this collaborative robotic future we've discussed.
What new opportunities are waiting to be uncovered for humans and machines to work together in novel ways? Not just to replace tasks, but to elevate human capabilities, to innovate processes, and ultimately to create entirely new possibilities for efficiency, safety, sustainability, and perhaps even human flourishing in the age of intelligent automation. It's a future that's arriving faster than many people think.